In December of 1900, a careful and rather conservative German physicist named Max Planck published a small mathematical trick. He had been trying to explain the colors of hot glowing objects. Nothing worked, and in the end, he simply assumed that energy came in discrete lumps rather than a smooth flow. He did not believe it. He called it an act of desperation and spent years trying to undo it. He had just written down the foundation of everything. Tonight we take that trick apart slowly and follow it down into the layer beneath ordinary things. Waves that are also particles. Objects in several places at once. Two things connected across any distance. This channel is on Spotify as well, if you would rather rest your eyes and let the sound carry you. The link is in the description. Tell me in the comments which corner of the world you are in and what your clock says. Let's go down there gently. Settle in. There is no rush at all in what follows. I want to say something at the start about how this is going to feel, because quantum physics has a reputation, and the reputation is not entirely fair. You have probably been told somewhere along the line that quantum mechanics is incomprehensible, that nobody understands it, that it is so strange that the human mind simply cannot hold it. There is a famous line from Richard Feynman along those lines, and it gets quoted so often that it has become a kind of permission slip to stop trying. I do not think that is quite right, and I would like to offer you a gentler version tonight. Quantum mechanics is not incomprehensible, it is unfamiliar. Those are different problems. Something incomprehensible has no handles on it at all. Something unfamiliar simply requires you to put down a set of expectations you have carried since childhood and to pick up a different set. And that takes time rather than genius. Every one of us learned physics before we could speak. A baby dropping a spoon from a high chair over and over is running an experiment. And what it learns is that objects have definite positions, that they fall, that they continue to exist when they roll under the table, and that they are in one place at a time. This is not a theory you were taught. It was installed in you by the world before language, and it has never once been wrong in your entire life. That is the thing we are setting down for the next 2 hours. Not because it is false, it is true, and beautifully so at the scale of spoons. It is simply not the deepest description, and the deeper one looks strange from where we are standing. We are going to go slowly. If you fall asleep somewhere in the middle, that is entirely the point, and the ideas will still be waiting whenever you come back. Let's begin with something in the room with you. If there is a lamp on nearby, look at it or picture one. An old-fashioned one, ideally, with a filament rather than a diode. Inside that bulb is a thin coil of tungsten wire, and electricity is being pushed through it, and the wire is resisting, and the resistance is making it hot. Very hot. A tungsten filament in an incandescent bulb runs somewhere around 2,500 degrees Celsius. And because it is hot, it glows. Notice that you are not surprised by this. Hot things glow. It is one of the oldest facts humans know. Every fire anyone has ever sat beside has demonstrated it. And we have been sitting beside fires for a very long time. But now think about the color. A poker left in a fire does not begin to glow at just any color. It warms and warms, and at first it emits nothing you can see, though you can feel the heat on your face from a distance. Then, at around 500 degrees, it begins to show a dull red. Push it hotter, and the red brightens to orange. Hotter still, and it goes yellow. A blacksmith's forge, pushed hard, gives white, and the hottest stars in the sky are blue. There is a strict, reliable relationship between how hot a thing is and what color it glows. It is so reliable that astronomers use it as a thermometer. When you look up and see that Betelgeuse in Orion is orange and Rigel in the same constellation is blue-white, you are reading their surface temperatures directly. Betelgeuse is around 3,500 Kelvin. Rigel is around 12,000. Every star's color is a temperature reading, and it works because the physics is universal. Here is the thing about that. Toward the end of the 19th century, physics could not explain it. Not approximately, not roughly. The best theory available gave an answer that was not merely wrong, but absurd, and the absurdity was so total that it broke the theory open. And the crack it made is where we are going tonight. But before the crack, let me set out the question underneath all of this, because otherwise the details will feel like a series of curiosities rather than one thing. The question is whether the world you experience is the bottom. You live at a particular scale. Your body is a bit under 2 meters. The objects you handle are centimeters to meters. The times you notice are seconds to years. Within that band, the world behaves in a way that feels like common sense, because common sense is precisely the set of rules that work in that band. And for most of human history, there was no reason at all to think anything else was going on. The world seemed to be made of smaller versions of the same kind of thing. Cut a rock in half, and you get 2 smaller rocks. Cut those, and you get gravel. Cut the gravel, and you get sand. Cut the sand, and you get dust. The Greek atomists guessed that this had to stop somewhere, and they were right about that, but they imagined the stopping point as a very small, hard pebble, a miniature ordinary object. What actually happens when you go down far enough is not that objects get smaller, it is that they stop being objects in the sense you mean. The rules change. Not slightly, completely. Position stops being a single value and becomes a spread of possibilities. Energy stops being continuous and comes in steps. 2 separate things can share a single description that cannot be split between them. And a question like where is it can turn out to have no answer at all until it is asked. That layer is underneath everything. It is underneath this room and underneath your body and underneath every star you have ever looked at. It has been running the whole time, silently, with perfect consistency for 13.8 billion years. We just could not see it because we are enormous. So, the glowing poker and the crack it made. To do physics properly on a glowing object, you need to simplify. Real objects are complicated. A poker reflects some light as well as emitting it, and its surface is uneven and its material matters. So physicists in the 19th century invented an idealization. An object that absorbs absolutely all radiation that falls on it, reflecting nothing, and which therefore emits radiation purely as a function of its temperature and nothing else. They called it a black body, which is a slightly unhelpful name, because a black body that is hot glows brilliantly. Black refers to the absorbing, not the appearance. In practice, you build one as a cavity. A hollow box with thick walls, heated to a uniform temperature with a very small hole in one side. Light entering the hole bounces around inside and essentially never finds its way out again, so the hole is a nearly perfect absorber, and the light that does emerge from the hole is a pure sample of the radiation inside the cavity, which depends only on the temperature. Physicists in Berlin built these things and measured them very carefully, and by the 1890s they had beautiful data. For any given temperature, you get a curve. Very little energy at long wavelengths, rising to a peak at some particular wavelength, then falling away again toward short wavelengths. Heat the cavity and the whole curve rises, and the peak slides toward the blue. That is the shape that explains why the poker goes red, then orange, then yellow, then white. Now, theory, classical physics at the time had two enormously successful pillars. Newton's mechanics, which described how objects move, and Maxwell's electromagnetism, which described light as waves in an electromagnetic field. Both were triumphs. Both had been tested exhaustively. Together they seemed to be very close to a complete account of nature, and a number of eminent people said so out loud, which is always unwise. Applying them to the cavity gave the following picture. Inside the box, the electromagnetic field can oscillate in a great many different patterns called modes, each one a standing wave fitting neatly between the walls. Thermodynamics said that in a system at thermal equilibrium, energy distributes itself evenly among all the available modes. Each mode gets an equal average share. That principle is called equipartition, and it works splendidly for gases. The trouble is counting the modes. Long wavelength modes are few because only so many long waves fit inside a box. But as you go to shorter and shorter wavelengths, the number of possible patterns grows and grows without limit. There is no shortest wavelength, so the number of modes is infinite. And if every mode gets an equal share of energy, and there are infinitely many modes, then the cavity contains infinite energy, and it radiates infinitely, and all of it at the short wavelength end. Lord Rayleigh, and later James Jeans, worked out the formula properly, and it matches the measurements beautifully at long wavelengths, and then rises without limit as the wavelength shrinks, which means that according to the best physics of the 19th century, opening the door of a warm oven should release a lethal blast of ultraviolet light and X-rays. The name for this failure, coined later by Paul Ehrenfest, is the ultraviolet catastrophe. It is one of the great phrases in science, and it is not an exaggeration. It is not that the theory was slightly off. The theory predicted infinity where the measurement gave a gentle hump. Enter Max Planck. Planck was 42 years old in 1900, and he was, by temperament, exactly the wrong person to start a revolution. He was born in Kiel in 1858 into a family of theologians and lawyers. He was a fine pianist who had seriously considered music as a career, and he was deeply, sincerely conservative in his physics. He believed in the absolute validity of thermodynamics. When he was a student, a professor advised him not to go into physics because essentially everything was already known, and there was nothing left but to fill in decimal places. Planck went into it anyway, but he went into it as a man who expected to tidy, not to demolish. He spent years on the black body problem. He tried everything conventional. Nothing worked. And then, in October of 1900, working partly backward from the data, he found a formula that fitted the measured curve perfectly across the whole range. The formula was right. He then had to work out why. And the only way he could derive it was by making an assumption he found frankly distasteful. He assumed that the little oscillators in the walls of the cavity could not absorb or emit energy in arbitrary amounts. They could only exchange energy in discrete packets, and the size of a packet was proportional to the frequency of the radiation. Energy equals a constant multiplied by frequency. The constant is now called Planck's constant, written as a lowercase h, and it has a value of about 6.626 times 10 to the minus 34 joule seconds. That is an almost unimaginably small number. 33 zeros after the decimal point before you reach the 6. It is the reason the whole quantum world stayed hidden from us. The graininess of nature is fine beyond anything our senses could resolve, but it is not zero, and that changes everything. Because if energy comes in packets whose size grows with frequency, then the high-frequency short-wavelength modes in the cavity require large packets, and at a given temperature there simply is not enough thermal energy sloshing around to pay for them. Those modes cannot be excited. They stay empty. The infinity vanishes. The curve bends over and comes down. The formula matches the data. Planck presented this to the German Physical Society in Berlin on the 14th of December 1900, and that date is usually given as the birthday of quantum theory. He did not celebrate. He described what he had done as an act of desperation, and he meant it. He wrote later that he had been willing to sacrifice any of his previous convictions about physics in order to make the numbers work. And for years afterward, he tried to find a way to derive his formula without the packets, to show that the graininess was some artifact of the mathematics rather than a real feature of nature. He never managed it. Nobody ever has. There is something quietly moving about that, I think. A cautious man in his 40s who wanted more than anything to preserve the physics he had grown up with, and who was honest enough to publish the thing that destroyed it, and who then spent a decade trying to take it back. He received the Nobel Prize in 1918. His later life was very hard. He lost his eldest son in the First World War, 2 daughters in childbirth, and his second son was executed in 1945 for involvement in the plot against Hitler. He stayed in Germany through all of it and worked to protect what he could of German science. He died in 1947, but in 1900 all that was ahead, and what he had on paper was a formula with a strange little constant in it that he did not believe. It took someone else to believe it. In 1905, a 26-year-old patent clerk in Bern published 4 papers in a single year, any one of which would have made a career. One was on special relativity. One derived the mass-energy relationship. One explained the jittery motion of pollen grains in water and gave the first convincing physical proof that atoms exist at all. And one, the first of the 4, took Planck's packets seriously. Albert Einstein's insight was to say something Planck had specifically avoided. Planck had suggested that the oscillators in the cavity walls exchanged energy in lumps, which he could just about tolerate as a property of matter. Einstein said the light itself is lumpy, not just its absorption and emission. The thing itself, a beam of light, is a stream of discrete energy packets traveling through space. This was, in 1905, close to heresy. The wave theory of light was not a guess. It had been established for 100 years and confirmed 1,000 times. Thomas Young had demonstrated interference in 1801. Augustin-Jean Fresnel had built the mathematics. Maxwell had unified light with electricity and magnetism in the 1860s and shown that light simply is an electromagnetic wave, and Heinrich Hertz had generated and detected such waves deliberately in the 1880s. The wave picture explained diffraction, interference, polarization, refraction, everything. Saying light was made of particles sounded like proposing to go back to Newton and undo the entire 19th century. But Einstein had a piece of evidence, and it was a good one. It is called the photoelectric effect, and it had been discovered by Hertz in 1887, ironically while he was confirming that light was a wave. If you shine light on a clean metal surface, electrons are knocked out of it. That in itself is unsurprising. Light carries energy, and energy can dislodge things. The details were the problem. On the wave picture, the energy in a light wave is spread out across the wavefront, and the brightness tells you how much energy is arriving. So a dim light should still eject electrons. It would just take longer for enough energy to accumulate at any one spot. And brighter light should eject faster electrons because each one is receiving more energy. Neither of those things happens. What actually happens is this. Below a certain frequency of light, no electrons come out at all, no matter how bright the beam. You can shine an enormously powerful red light on the metal for hours and nothing happens. Go above that frequency even with a very faint beam and electrons come out immediately. And the energy of the ejected electrons depends only on the frequency of the light, not on its brightness. Making the light brighter gives you more electrons, all with the same energy. Einstein's explanation was immediate once you accept the packets. Light arrives as individual quanta, each carrying an energy equal to Planck's, constant times the frequency. An electron in the metal is bound and needs a certain minimum energy to escape. It absorbs one quantum all at once, or it does not. If the quantum is too small, which is to say if the frequency is too low, then nothing happens, and it does not matter how many such quanta arrive, because they do not add up. 1,000,000 small payments do not equal one large one if each transaction must clear on its own. If the quantum is large enough, the electron escapes, and whatever energy is left over after paying the escape cost becomes the electron's kinetic energy. So a higher frequency means a faster electron. A brighter beam means more quanta, which means more electrons, each with the same energy as before. Every observed detail falls out of one assumption. The physics community did not accept this quickly. Robert Millikan, an experimentalist of the first rank, spent roughly a decade trying to prove Einstein wrong about it, and in 1916 published a set of measurements which confirmed the relationship in exquisite detail, in which he described in print as being at odds with his own expectations. He had disproved his own position with unusual thoroughness. Even in 1913, when Planck and 3 others nominated Einstein for membership of the Prussian Academy of Sciences, they wrote a recommendation praising him extravagantly, and then added essentially that he should not be held against too harshly for his speculation about light quanta, since one cannot introduce genuinely new ideas without occasionally missing the target. That is a remarkable thing to have written about what would become the man's Nobel Prize. Because when Einstein was awarded the Nobel Prize in Physics, announced in 1922 for the year 1921, the citation was not for relativity. Relativity was still considered too controversial, and there were people on the committee who did not like it. The prize was awarded for his services to theoretical physics, and specifically for his discovery of the law of the photoelectric effect. The most famous physicist in history received his Nobel for the paper about lumpy light. The word photon, incidentally, came much later. It was coined in 1926 by the American physical chemist Gilbert Lewis in a paper proposing a theory that was itself wrong, but the name stuck. So by around 1920, physics was in an uncomfortable position. Light was a wave. This was proven beyond argument by interference and diffraction. Light was a particle. This was proven beyond argument by the photoelectric effect. Both statements were supported by unambiguous experiment. Neither could be dropped, and they appeared to be flatly contradictory, because a wave is a spread out disturbance in a medium and a particle is a localized thing at a point, and nothing can be both. Physics sat with that contradiction for the better part of 2 decades. Before we go on, there is a second front in this story that was opening at the same time, and it concerns the most ordinary object in the universe, the atom. In 1911, at the University of Manchester, Ernest Rutherford was interpreting the results of an experiment carried out by Hans Geiger and a young student named Ernest Marsden. They had fired alpha particles at a very thin sheet of gold foil, expecting them to pass more or less straight through. Because the prevailing model of the atom imagined positive charge spread out diffusely with electrons embedded in it, rather like fruit in a pudding. Most did pass straight through, but a very small fraction came back, not deflected slightly, reversed. Rutherford described it later as being about as credible as firing a 15-inch shell at a sheet of tissue paper and having it bounce back at you. The only explanation was that almost all the mass and all the positive charge of an atom is concentrated in a tiny, dense core, with the electrons somewhere outside it and nearly everything in between being empty. That is the picture everyone carries in their head. A nucleus with electrons around it like a little solar system, and it has a fatal problem which Rutherford knew perfectly well. An electron moving in a circle is accelerating because its direction is constantly changing, and Maxwell's electromagnetism, which was not in any doubt, says that an accelerating charge radiates energy away as electromagnetic waves. An orbiting electron should therefore be pouring out light continuously, losing energy and spiraling inward. You can calculate how long it would take. The answer is around 10 picoseconds, 10 trillionths of a second. Every atom in the universe should have collapsed almost immediately after forming. There should be no matter. There should be nothing at all. The fact that you exist is a direct refutation of 19th century physics, and the refutation is very loud. There was a second clue, and it had been sitting in plain sight for 100 years. In 1814, a Bavarian optician named Joseph von Fraunhofer, who made the finest glass and prisms in Europe, was testing his instruments by spreading sunlight into a spectrum. He noticed that the smooth band of color was crossed by narrow dark lines. He counted and cataloged several hundred of them, mapped their positions carefully, and labeled the strongest with letters that are still in use. He had no idea what they were. He used them as reference marks. Half a century later in Heidelberg, Gustav Kirchhoff and Robert Bunsen worked out what they meant. If you heat an element until it glows and spread its light through a prism, you do not get a continuous rainbow. You get a set of specific bright lines at specific colors, and the pattern is different for every element and absolutely characteristic of it. Sodium gives its famous yellow pair. Hydrogen gives a red, a blue-green, and 2 violets. And if you shine white light through a cool gas, that same gas absorbs at exactly the wavelengths it would emit, leaving dark lines in the spectrum. Fraunhofer's dark lines were the fingerprints of the elements in the sun's outer atmosphere. This was one of the most consequential discoveries in all of science because it meant that the composition of objects unimaginably far away could be read directly from their light. Astronomy became chemistry. In 1868, during a solar eclipse, Pierre Janssen and Norman Lockyer independently observed a yellow line in the sun's spectrum that matched no known element on Earth. Lockyer proposed it belonged to a new element and named it after the Greek word for the sun. Helium was discovered in a star 27 years before anyone found it on this planet. But nobody knew why elements produced lines at all. Why should hydrogen glow at those particular colors and no others? A Swiss schoolteacher named Johann Balmer, in 1885 at the age of 60, found a simple formula that fitted the visible hydrogen lines beautifully. It worked perfectly, and it explained nothing. It was numerology that happened to be right. Both problems were solved at once in 1913 by a 28-year-old Dane. Niels Bohr had come to Manchester to work with Rutherford, and he made a proposal that was frankly outrageous by the standards of the time. He said that electrons in atoms may only occupy certain specific orbits with certain specific energies, and that while in one of those orbits an electron simply does not radiate. He offered no mechanism for this. He asserted it because it made the atom stable. And then he said that an electron can jump from one allowed orbit to another, and when it does, the difference in energy is emitted or absorbed as a single quantum of light, with a frequency given by Planck's relation, which means the light an atom emits can only have certain energies, which means certain frequencies, which means certain colors, which means spectral lines. Bohr calculated the allowed energies for hydrogen from first principles, took the differences, and out fell Balmer's formula, with the constant in it emerging correctly from Planck's constant, the electron mass and the electron charge, a number that had been an empirical curiosity for 28 years was suddenly derived. That was the moment a great many people started paying attention. The Bohr model is, strictly speaking, wrong. It does not work properly for atoms with more than one electron, and its picture of electrons on tracks is not what modern quantum mechanics says. But it was right about the essential thing, which is that atoms have discrete energy levels, and that light comes from transitions between them, and that idea has never been overturned. Bohr received the Nobel Prize in 1922, the year before Einstein collected his, and there is a lovely postscript. Bohr never explained why only certain orbits were allowed. It was a rule, with no reason underneath it. The reason arrived from de Broglie. If an electron is a wave, then an orbit is only stable if a whole number of wavelengths fits neatly around it so that the wave joins up with itself smoothly instead of canceling itself out, like a plucked string, which can only vibrate at certain frequencies because the ends are fixed. Bohr's arbitrary allowed orbits are the harmonics of a standing wave. The atom is a musical instrument, and the colors of every star in the sky are the notes it can play, which brings us to the French graduate student who made everything very much stranger. Louis de Broglie was born in 1892 into one of the oldest aristocratic families in France. His full title, which he eventually inherited from his brother, was the 7th Duc de Broglie. He began his studies in history intending a career in the diplomatic service and drifted into physics, partly through the influence of his much older brother Maurice, who ran a private laboratory in the family mansion in Paris and worked on X-rays. X-rays were, at that time, a live example of the wave-particle puzzle. They diffracted like waves, and they knocked electrons out of atoms like particles. Louis grew up around dinner table conversations about it. In 1924, he submitted a doctoral thesis containing an idea of almost childlike symmetry. Physics had spent 20 years discovering that light, which everyone knew was a wave, also behaves as a particle. De Broglie asked the obvious reverse question: what if matter, which everyone knows is particles, also behaves as a wave? He proposed that every material object has a wavelength associated with it and gave the formula. The wavelength equals Planck's constant divided by the momentum of the object. That is a very short formula, and it has an enormous consequence. Because Planck's constant is so tiny, and because momentum is mass times velocity, The wavelength of anything ordinary is preposterously small. A tennis ball traveling across a court has a de Broglie wavelength around 10 to the minus 34 meters, which is unmeasurably, unimaginably smaller than an atomic nucleus. There is no experiment that could ever detect it, and so a tennis ball behaves exactly like a tennis ball forever. But an electron is about 9 times 10 to the minus 31 kilograms. Nothing. And if you accelerate one through a modest voltage, its de Broglie wavelength comes out at around a tenth of a nanometer, which happens to be roughly the spacing between atoms in a crystal, which means that if de Broglie was right, a crystal should diffract electrons the way a diffraction grating diffracts light. His thesis examiners in Paris were not sure what to make of it. It was a very short thesis by the standards of the time. It contained no experimental evidence, and it made a claim that sounded like wordplay. Paul Langevin, one of the examiners, sent a copy to Einstein and asked for an opinion. Einstein wrote back that de Broglie had lifted a corner of the Great Veil. The thesis was accepted. 3 years later, it was confirmed twice, independently on 2 continents. And one of the confirmations was an accident. At Bell Telephone Laboratories in New York, Clinton Davison and Lester Germer were firing electrons at a nickel target and measuring how they scattered. In 1925, a liquid air bottle exploded in the laboratory. Air rushed into their vacuum system, and the nickel target oxidized badly. To clean it, they heated it strongly for a long period, and in the process, the nickel, which had been a fine-grained polycrystalline lump, recrystallized into a small number of large crystals. When they resumed the experiment, the scattering pattern had completely changed. Instead of a smooth spread, the electrons were coming off in sharp preferred directions. It took them until 1927 to understand what they had. The electrons were diffracting from the regular rows of atoms in the newly formed crystals, exactly as de Broglie's formula predicted, with the peaks at exactly the angles the wavelength required. In the same year, at the University of Aberdeen, George Paget Thomson fired electrons through very thin metal foils and photographed the rings of a diffraction pattern on the far side. There is a lovely piece of family history in that. George Paget Thomson's father was Joseph John Thomson, who in 1897 had discovered the electron and demonstrated that it was a particle, and who received the Nobel Prize for it in 1906. The father proved the electron was a particle. The son proved it was a wave. Both were right. Both received Nobel Prizes, 31 years apart. De Broglie received his in 1929, 5 years after the thesis. So now the situation was not that light was strange. The situation was that everything was strange. Matter and light were both doing this. Electrons, protons, neutrons, atoms, and as we will see, molecules with thousands of atoms in them. Which brings us to the experiment at the center of all of this. If you take away only one thing from tonight, let it be this one, because everything else in quantum mechanics is in some sense a footnote to it. Let me build it slowly. In 1801, Thomas Young, an English physician and polymath, who among other things did foundational work on how the eye focuses and helped decipher Egyptian hieroglyphs, performed a demonstration at the Royal Institution in London. He let sunlight through a small hole to make a narrow beam, and then placed in its path a card with 2 thin parallel slits cut in it very close together. Behind the card he put a screen. Common sense predicts 2 bright lines on the screen, one behind each slit. What appeared was a series of many bright and dark bands, spread out across the screen, with the brightest in the middle, directly between the 2 slits, where by the common sense prediction there should be nothing at all. This is interference, and it is a signature of waves, and you have seen it in water without necessarily noticing. Drop two stones into a still pond at the same moment. Two sets of ripples spread out and cross each other. Where a crest from one meets a crest from the other, they add and you get a bigger crest. Where a crest meets a trough, they cancel and the water is flat. The result is a pattern of alternating lines radiating out through the region where the two wave systems overlap. Young's bands are exactly that in light. Each slit acts as a fresh source of waves. The two sets of waves overlap, and where crests coincide, you get brightness, and where crest meets trough, you get darkness. That experiment ended the argument about whether light was a wave, and it stood unchallenged for a century. Now do it with electrons. The first true electron double-slit experiment was performed by Klaus Jönsson in Tübingen in 1961, which is remarkably late. It is genuinely difficult to make slits fine enough. He produced the interference pattern. Fine. Electrons are waves. De Broglie said so. The pattern is expected. Now slow the source down. This is where it becomes something else entirely. Turn the electron source down so low that only one electron is in the apparatus at any given moment. One electron leaves the gun. It crosses the apparatus. It hits the detector. Only then does the next one leave. There is never more than one electron in flight. Nothing can interfere with anything because there is nothing else present. Each electron arrives at the detector as a single point, a dot, a flash at one specific location. It is unambiguously a particle when it arrives. It does not spread out and dampen the whole screen. It lands in one place and it deposits its whole energy there. The dots appear to be scattered randomly. 10 electrons look like noise. 100 look like noise. A few hundred, and you might begin to suspect something. And then, as the dots accumulate into the thousands and tens of thousands, the interference pattern emerges out of them. Bands. Bright regions where many electrons landed, dark regions where almost none did, in exactly the positions the wave calculation predicts. Each electron went through alone. Each arrived as a point. And yet the collection of points knows about both slits. The individual electron, in some sense that resists ordinary language, went through both. This was done properly with single electrons in 1974 by Pier Giorgio Merli, Gianfranco Misiroli, and Giulio Pozzi in Bologna, and again in a beautifully clean version in 1989 by Akira Tonomura and colleagues at Hitachi in Japan. The Hitachi film, which shows the dots landing one at a time and the pattern slowly assembling itself out of apparent randomness, is one of the genuinely great documents of 20th century science. In 2002, the readers of Physics World voted the single electron double slit the most beautiful experiment in physics. And now the part that makes people go quiet. Put a detector at the slits. Any device that tells you which slit each electron passed through. This is not a thought experiment. It has been done in many forms. The interference pattern disappears. You get two bands. The common sense answer. Exactly what you would expect from small pellets going through one hole or the other. Turn the slit detector off and the interference comes back. Nothing else has changed. Same source, same slits, same screen, same electrons. The only difference is whether information about the path exists. If the which path information exists anywhere, the electron behaves like a particle taking one route. If it does not exist anywhere, the electron behaves like a wave taking all routes. And the experiment can be pushed further into territory that seems to defy the ordering of events. Delayed choice experiments, proposed by John Archibald Wheeler in 1978 and performed in various forms since, arrange for the decision about whether to record which path information to be made after the particle has already passed the slits. The result is always consistent with whatever measurement configuration finally exists, not with the configuration at the moment of passage. This does not mean the future changes the past. That is a tempting reading, and it is not what the mathematics says. What it means roughly is that the story you tell about what the particle did between emission and detection is not a description of events. It is a description that only becomes definite when the whole experimental arrangement is accounted for, and the particle does not have a hidden itinerary that we simply failed to read. And the effect is not confined to electrons. It has been demonstrated with photons, with neutrons, with whole atoms. In 1999, a group in Vienna, including Marcus Arndt and Anton Zeilinger, sent Buckminster fullerene molecules through a grating and got interference. A buckyball is 60 carbon atoms arranged in a hollow sphere. It is a genuine object, a thing you could in principle photograph with an electron microscope. And it interfered with itself. They kept going. Larger molecules, then larger still. The current record held by Arndt's group in Vienna is molecular interference with objects of around 25,000 atomic mass units, made of roughly 2,000 atoms. 2,000 atoms. Held in a state where they passed through more than one path at once. There is no known upper limit in the theory. There is only an engineering limit, which is that the bigger the object, the harder it is to keep it isolated from everything else, and we will come to why that matters enormously. Let me try an image for this because the mathematics is precise and the words are clumsy, and the words are what we have tonight. Imagine a question that has no answer until it is asked. Not a question whose answer is hidden, not a question whose answer you have forgotten, a question that genuinely does not have an answer, sitting somewhere waiting to be discovered. Think of a piece of music you love but have not thought of in years. Before you brought it to mind just now, where was it? Not in your ears, not playing anywhere. It was not sitting somewhere in your head as a finished recording waiting to be pressed play on. What was there was a pattern of connections, a potential, a structure capable of producing the music, but not currently producing it. And the moment you attended to it, something definite came into being that had not been definite a second earlier. Now that is only an analogy, and I want to be careful with it because a memory is not a quantum system, and the resemblance is poetic rather than physical. But it points at the right shape of the strangeness. Our deepest instinct is that things have properties, and that measurement is the act of finding out what those properties already are. You put a thermometer in the bath to discover the temperature the bath already had. You open the box to see which sock is inside, and the sock was that color all along. What the double slit is telling us is that at the smallest scale, this is not how it works. Some properties are not sitting there waiting to be found. They are brought into definiteness by the interaction that reveals them. Before that, what exists is not a hidden value but a spread of possibility, and the spread itself is real. And it is the spread that interferes with itself and produces the bands. The electron did not take a secret path we failed to observe. There was no fact of the matter about which path it took. That is a very hard sentence to accept, and Einstein never accepted it. And we will get to his objection because it produced the most beautiful chapter in the whole story. But first, we need to talk about what the spread of possibility actually is mathematically, because it has a name and a very precise description, and understanding it removes a great deal of the mystique. In the winter of 1925, an Austrian physicist named Erwin Schrödinger went on holiday. He was 38, working in Zurich, and by the standards of theoretical physics, he was old to be doing revolutionary work. The field at the time was full of people in their early 20s, and the whole period was later nicknamed the boys' physics. He went up to a villa in Arosa in the Swiss Alps over Christmas and the New Year, accompanied by a woman who was not his wife, whose identity has never been established. He came back down with a wave equation. The Schrödinger equation describes how the wave associated with a particle evolves through time. It is a differential equation, and it is not especially exotic as mathematics goes. Anyone who has studied physics or engineering at university has solved equations of that general family. It is deterministic, it is smooth, it is continuous, and given the state of a system now, it tells you the state at any later time. Exactly. That is worth sitting with. The core equation of quantum mechanics is not random. It is as deterministic as Newton's laws. The randomness comes in somewhere else, and it comes in at the moment of measurement, and that is the whole difficulty. Schrödinger's equation has a solution, a mathematical object usually written with the Greek letter psi and called the wave function. And here is the question that occupied everyone. What is it? Schrödinger himself initially thought it was literally the particle, that an electron was not a point at all, but a smeared out cloud of substance, and the wave function described the actual physical density of that cloud. It is an appealing idea, and it explains why electrons and atoms sit in stable orbits, since only certain wave shapes fit around a nucleus without canceling themselves out, but it does not survive contact with the double slit. When an electron hits a detector, it does not arrive as a smear. It arrives as a point all in one place with all its charge and all its energy delivered right there. The answer came in June of 1926 from Max Born working in Göttingen, and it arrived in one of the great footnotes in the history of physics. Born wrote a paper on the scattering of particles, and in it proposed an interpretation, and then, in the proofs, added a correction in a footnote that made the interpretation correct. The wave function is not a physical substance. Take its magnitude and square it, and what you get is a probability density. It tells you the likelihood of finding the particle at each location if you look. The wave is a wave of probability. That is why the electron in the double slit can interfere with itself and still land as a dot. The probability wave goes through both slits. The two parts of it overlap on the far side and interfere, producing regions of high probability and regions of near zero probability. Then the electron is detected and it appears at one location chosen from that distribution. Fire enough electrons and the distribution becomes visible as a pattern of dots. Born received the Nobel Prize for this in 1954, 28 years later, which is an unusually long wait and reflects how contested the interpretation was, because a great many people hated it. Einstein hated it, and his objection is the famous one, usually quoted as, "God does not play dice," which is a slight compression of what he actually wrote to Born in a letter in 1926. His real position was more interesting than the slogan. He did not object to probability as such, since he had used statistical methods brilliantly himself. He objected to probability being fundamental. He thought it must be a sign that the description was incomplete, that there were deeper variables underneath that would restore definiteness, the way the apparently random motion of a gas is really the deterministic motion of countless molecules. Schrödinger hated it too. He is supposed to have said that he did not like it and was sorry he ever had anything to do with it. Which brings us to the cat, and I want to correct something about the cat because it is almost universally misunderstood. In 1935, Schrödinger published a long paper in the journal Naturwissenschaften called The Present Situation in Quantum Mechanics. In it, he describes a scenario. A cat is sealed in a steel chamber with a small quantity of radioactive material, so small that over the course of an hour there is an even chance that one atom decays. If an atom decays, a detector triggers a hammer, which shatters a flask of hydrocyanic acid, and the cat dies. The radioactive atom, being a quantum system, is in a superposition of decayed and not decayed. And since the cat's fate is entangled with the atom, the standard formalism would seem to put the cat in a superposition of alive and dead. Schrödinger was not proposing this as a wonder. He was not saying, "Isn't quantum mechanics marvelous?" He was writing a complaint. He was pointing out that if you take the standard interpretation absolutely literally and scale it up, you arrive at a description that is obviously ridiculous, and that the ridiculousness indicates something is missing from our understanding. The cat was intended as a reductio. It was a criticism, and it has spent 90 years being cited as a celebration of the very thing it was attacking, which is one of the more ironic outcomes in the history of ideas. In the same paper, Schrödinger introduced a word for the connection between the atom and the cat. In German, he wrote Verschränkung. In English, it became entanglement, and he described it not as one interesting feature among many, but as the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. We will come to entanglement properly, because it is the deepest thing in this whole subject, and because settling it took 50 years and a Nobel Prize awarded in 2022. But there is one more piece of the foundation to lay first, and it is the one people misunderstand more often than any other. In June of 1925, a 23-year-old German physicist named Werner Heisenberg was suffering badly from hay fever. His face was so swollen that his landlady assumed he had been in a fight. He took 2 weeks' leave and traveled to Helgoland, a small rocky island in the North Sea with almost no vegetation on it and therefore almost no pollen. He spent the fortnight walking, swimming, memorizing poetry, and working. What he produced there was a completely new formulation of mechanics, built on a strict principle. He decided to refuse to talk about anything that could not be observed, not the orbit of an electron inside an atom, because nobody had ever seen one. Only the things you can actually measure, which are the frequencies and intensities of the light atoms, emit and absorb. He arranged those observable quantities into tables. When he worked out how to multiply them together, he found that the answer depended on the order. Table A times table B did not give the same result as table B times table A. He thought at first he had made an error because ordinary numbers do not behave like that. 3 times 5 and 5 times 3 are the same. He had not made an error. He had rediscovered, without knowing it, the mathematics of matrices, which Max Born recognized when Heisenberg brought the work back to Göttingen. Born and Pascual Jordan developed it, and matrix mechanics became the first complete formulation of quantum theory, several months before Schrödinger's wave equation. The two turned out to be mathematically equivalent, describing the same physics in different clothes. That non-commuting multiplication, where order matters, is not a quirk. It is the mathematical root of the thing Heisenberg published 2 years later, in March of 1927. The uncertainty principle. In its usual form, it says that the uncertainty in a particle's position multiplied by the uncertainty in its momentum cannot be smaller than a particular tiny quantity related to Planck's constant. Know the position very precisely and the momentum becomes correspondingly vague. Pin the momentum down and the position spreads out. Now here is the misunderstanding, and it is nearly universal, and Heisenberg himself is partly to blame for it. In his original paper, he explained the principle with a thought experiment about a microscope. To see where an electron is, you must bounce something off it, and the only things available are photons, and a photon carries momentum, so hitting the electron with one changes its motion. The more precisely you want to locate it, the shorter the wavelength of light you need, and shorter wavelength means higher energy, which means a bigger kick. That story is intuitive, and it is memorable, and it is wrong, or at least it is describing a different effect. Niels Bohr, who was Heisenberg's mentor and could be relentless, spent weeks arguing with him about it, to the point where Heisenberg is said to have been reduced to tears. Bohr's objection was that the disturbance picture makes it sound as though the electron really does have a definite position and a definite momentum, and our clumsy instruments merely spoil our knowledge of them. That is not what the mathematics says. The mathematics says the electron does not possess both properties simultaneously with arbitrary precision. It is not a limit on knowledge. It is a statement about what there is to know. And once you see it as a property of waves, it stops being mysterious at all. It becomes almost obvious. Think about sound. Play a note on a violin and hold it. A long, steady note has a definite pitch. You could tell me its frequency, and a tuner would agree because the wave repeats regularly for a long time and its frequency is well defined. Now, instead of a note, make a click. A single sharp tap on a table. What pitch is a click? The question does not really have an answer. A click is very well localized in time. You can say precisely when it happened, but it has no definite frequency at all. If you analyze it, a click contains a broad smear of frequencies all at once. That is not a limitation of your ears or your equipment. It is what a click is. A sound cannot be both instantaneous and a pure tone, because a pure tone requires many repetitions to exist as a tone. Time and frequency trade off against each other in sound, and this is old and well understood mathematics that has nothing to do with quantum theory. It is why a tuner needs a moment to settle. It is why very short musical notes sound pitchless and percussive. Now put de Broglie's relation on top of it. In quantum mechanics, momentum is frequency. They are the same thing related by Planck's constant. So position and momentum trade off against each other for exactly the same reason that timing and pitch do. A particle with a very definite position is a sharp pulse, and a sharp pulse is built from a wide range of wavelengths, which means a wide range of momenta. A particle with a very definite momentum is a long regular wave, and a long regular wave is spread out over space. Nothing is being disturbed. Nothing is being hidden. It is simply that these two quantities are two faces of one wave, and you cannot make both faces sharp. There is a companion relation between energy and time, and it has a spectacular consequence. Over very short intervals, the energy of a system is correspondingly undefined, which means that empty space is not empty. In the vacuum, pairs of particles can appear and annihilate again, borrowing energy for an interval short enough that the uncertainty relation permits it. This is not a metaphor. It has measurable consequences. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed extremely close together in a vacuum would be pushed toward each other because the gap between them excludes some of the possible vacuum fluctuations, while the outside does not, leaving a net pressure inward. It was measured directly by Steve Lamoureux in 1997 and has been confirmed many times since. Empty space pushes on things because of uncertainty. And the same vacuum activity near the edge of a black hole is the origin of Hawking radiation, which is how black holes very slowly evaporate. The rules beneath reality reach all the way up to the largest and darkest objects in the universe. Now let's go to the deepest one. In 1935, Einstein, then at the Institute for Advanced Study in Princeton, published a paper with two younger colleagues, Boris Podolsky and Nathan Rosen. It appeared in the Physical Review in May, and its title was a question. Can quantum mechanical description of physical reality be considered complete? Einstein's answer was no, and the paper was an attempt to prove it. The argument in the cleaner form, later given by David Bohm, goes like this. Certain processes produce two particles together in a way that correlates their properties. Take spin, which is a quantum property of particles that behaves somewhat like a tiny magnetic orientation. You can prepare a pair of particles such that their spins must be opposite. If one is measured as up along some axis, the other must be down along that axis. Conservation laws require it. Now separate them. Send one to a laboratory here and the other to a laboratory a long way away. Any distance you like. The correlation persists. Measure the near particle along the vertical axis. Suppose you get up, you now know instantly that the distant particle will give down if measured along the same axis. Fine so far. That is not mysterious by itself. Einstein's point was this. Either the distant particle already had the value down all along, and your measurement simply revealed a pre-existing fact about your own particle, in which case quantum mechanics is incomplete because it does not include those pre-existing values. Or the distant particle genuinely had no definite spin until the moment you measured yours, in which case your measurement here somehow determined the state of a particle over there instantly at any distance. The second option Einstein called. In a letter to Born, Spukhaft Fernwirkung, spooky action at a distance, he regarded it as absurd because it seemed to violate the principle that nothing propagates faster than light. So, he concluded, the first option must be correct. The particles carry hidden variables, little instruction sets, established at the moment they were created, and quantum mechanics simply fails to describe them. Just as a pair of gloves separated into two sealed boxes and shipped to opposite ends of the earth are correlated, and opening one box tells you instantly about the other, and there is nothing spooky about it at all, because each glove was always left or right. Bohr responded. The exchange was inconclusive, and for nearly 30 years, the whole question was regarded as philosophy rather than physics, a matter of taste about which no experiment could decide. It was not a respectable thing to work on. Physicists who were interested in it were quietly advised that it would damage their careers, and in several cases it did. Then, in 1964, a physicist named John Stuart Bell did something nobody had thought possible. Bell was Northern Irish, born in Belfast in 1928 to a family without much money. He left school at 16 and worked as a laboratory technician at Queen's University before being able to enroll as a student. He spent his career at CERN in Geneva working on accelerator physics, and he thought about quantum foundations, as he put it, on the side, as a hobby. He was on sabbatical in the United States when he wrote the paper that made him famous. It is 9 pages long. It is titled On the Einstein-Podolsky-Rosen Paradox, and it appeared in an obscure journal called Physics that folded shortly afterward. What Bell realized is that the hidden variable idea makes a prediction that differs from quantum mechanics. Not in the simple case where both experimenters measure along the same axis and always get opposite results. Both theories agree there. The difference appears When the two experimenters measure along different axes, chosen independently, and you look at the statistics of the correlations over many runs. Bell proved, with a piece of reasoning that requires no quantum mechanics at all, that any theory in which the particles carry pre-existing local instruction sets must obey a certain inequality. The correlations cannot exceed a specific bound. This follows from logic and arithmetic alone, and it holds regardless of what the hidden variables are or how complicated they might be, and quantum mechanics predicts a violation of that bound. So it was not philosophy after all. It was an experiment, a hard, decidable laboratory question about the nature of reality, with two possible answers and a number to measure. That is one of the most beautiful things any physicist has ever done. The experiments began. Stuart Friedman and John Clauser at Berkeley did the first serious test in 1972 using photon pairs emitted by calcium atoms. The result violated the inequality, siding with quantum mechanics. Though there were loopholes, the detectors were inefficient, so you had to assume the detected photons were a fair sample. In 1981 and 1982, Alain Aspect and his colleagues at Orsay near Paris did much better. Their key improvement was to switch the orientation of the analyzers while the photons were already in flight, using acousto-optical devices operating fast enough that no signal traveling at light speed could have carried the setting from one side to the other in time. This closed the locality loophole. The inequality was violated decisively. Anton Zeilinger's group in Vienna and elsewhere pushed further, sending entangled photons through kilometers of fiber and open air, demonstrating quantum teleportation of states, and eventually distributing entanglement between ground stations more than 1,000 kilometers apart using the Chinese satellite Metis in 2017. And in 2015, 3 independent groups at Delft in the Netherlands, at NIST in Boulder, Colorado, and in Vienna performed loophole-free tests, closing the detection loophole and the locality loophole simultaneously. The Delft experiment used electron spins in diamond defects separated by 1.3 kilometers across the university campus. All of them violated the inequality. In 2018, a group ran what they called a cosmic bell test, using the color of light from 2 distant quasars emitted billions of years ago to choose the measurement settings. If there was some conspiracy determining the settings in advance, it would have had to be arranged before the Earth existed. The inequality was still violated. In October 2022, Alain Aspect, John Clauser, and Anton Zeilinger shared the Nobel Prize in Physics for this body of work. So what does it mean? It means Einstein's preferred option is dead. There are no local hidden variables. The particles are not carrying secret instruction sets established at their creation. Whatever is happening, it is not the gloves in the boxes. The correlations are real, they are stronger than any local explanation permits, and they persist over any distance yet tested. Now, I want to be very careful here, because this is the point at which a great deal of nonsense gets attached to quantum mechanics, and you deserve the honest version. Entanglement does not let you send messages faster than light. This is not a practical limitation. It is provable, and the result has a name, the no communication theorem. Here is why. When you measure your particle, you get a random result, up or down, 50-50, with no way to control which. Your distant partner also gets a random result. Each of you, looking only at your own data, sees nothing but a random string. Nothing you do at your end changes the statistics at their end in any way they could detect. The correlation only appears when the two of you bring your lists of results together and compare them line by line. And to compare them, you have to send the lists to each other by radio or letter or telephone at ordinary speeds, no faster than light. The connection is real. The correlation is stronger than any classical arrangement allows, and it carries no information. That is a genuinely strange combination, and it is one of the reasons the interpretation is still argued about. Nature appears to be doing something non-local and simultaneously refusing to let us use it for anything non-local. It is as though the universe permits a connection that no local story can account for, and then arranges matters so that nobody can ever use it to send so much as a single bit. Now we come to the word that has caused more confusion than any other in this subject, and I would like to take it apart carefully, because getting it right actually makes the universe feel larger rather than smaller. The word is observation. You will have heard it said that in quantum mechanics, observing something changes it. That reality does not settle down until it is observed. That consciousness collapses the wave function that the universe requires a mind to make it real. The physics does not say this. It never did. The confusion is entirely historical, and it comes from the vocabulary the founders happened to use in the 1920s. They were experimentalists describing what they did in a laboratory, and what they did was observe. So the mathematics acquired a step called measurement, and measurement sounds like something that requires a measurer, and a measurer sounds like a person. But look again at the double slit. Put a detector at the slits, and the interference vanishes. Nobody has to read the detector. You can build the apparatus so that the witch path information is recorded onto a device that is then sealed in a box and never examined by anyone, and the interference is still gone. You can arrange for the information to be carried away by a single scattered photon that flies off into the darkness and is never captured. Gone. The pattern does not care whether a human being ever learns anything. What matters is not knowledge. What matters is whether the system has become correlated with anything else in the world. That process has a name, and it is one of the most important developments in the understanding of quantum mechanics in the last 50 years. It is called decoherence, and it was worked out principally in the 1970s and 80s by physicists including Heinz-Dieter Zeh in Heidelberg and Wojciech Zurek at Los Alamos. Here's the idea, gently. Interference happens when the different possible paths of a system remain, in a technical sense, indistinguishable. The wave function has multiple parts, and those parts can add and cancel because there is nothing anywhere in the universe that records which part is which. The moment any part of the environment becomes correlated with one branch rather than another, that indistinguishability is broken. A photon bounces off the particle and flies away carrying the information. An air molecule collides with it. A vibration in the apparatus registers it. And once that information exists out in the world, spread across countless degrees of freedom that nobody could ever gather back together, the branches can no longer interfere. The superposition has not been destroyed exactly. It has been leaked. It is spread out into the environment where it becomes, for all practical purposes, permanently inaccessible. And this happens extraordinarily fast for anything large. Calculations of decoherence times give numbers that are hard to hold in the mind. A dust grain, 1/100th of a millimeter across, floating in ordinary air, decoheres in something like 10 to the minus 31 seconds. Even in the best laboratory vacuum, with only the cosmic microwave background photons striking it, a small object is measured by its environment continuously and relentlessly, which answers the question everyone asks. Why is my chair not in a superposition of places? Because the chair is being touched constantly by air molecules and photons in the floor, and each touch records its position. And the recording has been spreading outward into the universe since long before you were born. The chair is the most thoroughly observed object in the room, and nobody is looking at it. This is why quantum computers are so difficult to build. The whole engineering challenge is to keep a system in superposition, which means keeping it perfectly isolated from everything, while simultaneously being able to manipulate it and read it out, which requires it not to be isolated at all. Machines are cooled to a few thousandths of a degree above absolute zero and shielded elaborately, and the fragile states still last for microseconds. It also explains the molecule interference results we talked about earlier. Sending a 2,000 atom molecule through a grating in a superposition of paths is not hard because of some law forbidding large objects from doing it. It is hard because you must keep the molecule from emitting a single thermal photon that would give away its position. Arndt's group cools the molecules and works in extreme vacuum for exactly this reason. So the honest summary is this: reality does not need a mind. The moon is there when nobody is looking. It is there because it is in continuous conversation with sunlight and with the Earth's gravity and with the solar wind, and that conversation is what makes it definite. The universe was doing this perfectly well for 9 billion years before there was anyone to notice, and I find that far more beautiful than the mystical version, because it means the strangeness is not about us at all. We are not special. We are just very large, very warm, very entangled objects living deep inside a regime where the quantum behavior has been thoroughly leaked away, which is why the world looks the way it does to us. The quantum layer did not go away. We are simply too well connected to everything to notice it. Now let me show you what that layer is doing while you sleep tonight, because it is doing a great deal. Start with the fact that you are not falling through your bed. That sounds like a joke, and it is not. Solidity is a genuine puzzle, and the answer is entirely quantum. An atom is mostly empty. If you scaled a hydrogen atom up so that its nucleus was the size of a marble, the electron cloud would be a sphere a few hundred meters across, with nothing in between but field. By volume, ordinary matter is something like a part in a trillion actual substance. So why does anything feel solid? Not because of electrical repulsion between electrons, which is part of the story, but nothing like the whole of it. The main reason is a rule discovered by Wolfgang Pauli in 1925, and it is the strangest law in the whole of physics. Particles come in two families. One family, which includes photons, is perfectly happy to pile up. Any number of them can occupy the same state at the same time. The other family, which includes electrons, protons, and neutrons, and therefore all the matter you are made of, absolutely cannot. No two of them may occupy the same quantum state simultaneously. That is the Pauli exclusion principle, and there is no deeper explanation of it in ordinary terms. It follows from a deep symmetry in how identical particles are described, and it is as fundamental as anything we know. It is why atoms have structure. Electrons in an atom cannot all fall into the lowest energy level. Once a level is full, the next electron must go into a higher one. That stacking is what produces electron shells, which produces the entire periodic table, which produces chemistry, which produces every substance you have ever touched, including yourself. The whole of chemistry is a consequence of a rule about what states particles are forbidden to share, and it is why solid things resist. Press two objects together and you are trying to force their electron clouds into the same region, which would require electrons to enter states already occupied. They refuse. The resistance you feel is not really a force in the ordinary sense. It is the cost of the exclusion, and it is enormous. The chair holds you up because of a quantum rule about identity. And that same rule holds up stars. When a star like the sun exhausts its nuclear fuel, gravity begins to win. The core contracts. Ordinarily, nothing could stop it. But as the electrons are squeezed closer and closer together, exclusion begins to bite. They cannot occupy the same states, so they are forced into higher and higher momentum states, and that produces an outward pressure that has nothing to do with heat at all. It is called electron degeneracy pressure, and it can hold up an object the mass of the sun compressed into a sphere the size of the Earth. That object is a white dwarf, and there are many billions of them in our galaxy, and our own sun will become one in about 5 billion years. In 1930, a 19-year-old Indian student named Subramanian Chandrasekhar worked out the mathematics on the ship carrying him from Madras to England to begin his doctorate. He found that degeneracy pressure has a limit. Above about 1.4 times the mass of the sun, the electrons must move so fast that relativity enters the calculation, and the pressure can no longer keep up with gravity. That number is now called the Chandrasekhar limit. When he presented it in London, Arthur Eddington, the most eminent astrophysicist of the age, ridiculed it publicly and said there ought to be a law of nature to prevent a star behaving so absurdly. Chandrasekhar was humiliated and eventually moved to the United States. He was right and Eddington was wrong, and he received the Nobel Prize for it in 1983, 53 years later. Above that limit, the collapse continues. Electrons and protons are crushed together into neutrons, and neutron degeneracy takes over, producing an object with the mass of a star and the diameter of a city. Push past that and nothing holds, and you get a black hole. The entire life story of a dying star is written in a rule about which quantum states particles may share. And there is one more, and it is the one that lets stars live in the first place. Look at the sun. It is a ball of hydrogen, and it shines because in its core, hydrogen nuclei fuse into helium, releasing energy. This has been happening for 4.5 billion years and will continue for about 5 billion more. There is a problem with this, and it was recognized in the 1920s, and it is severe. 2 hydrogen nuclei are 2 protons, and protons carry positive charge, and like charges repel. To fuse, they must be brought close enough for the strong nuclear force to take hold, and the strong force only acts across a distance of about a femtometer, a millionth of a billionth of a meter. Getting that close means climbing an enormous electrostatic barrier. The temperature at the center of the sun is around 15 million Kelvin. That sounds like it should be plenty. It is not. Do the calculation classically, and the protons in the solar core simply do not have enough energy to surmount the barrier, not the average ones, and not the fastest ones in the tail of the distribution either. The gap is not marginal. Classically, the sun should not be able to fuse hydrogen at all. The sun should not work. The resolution came from George Gamow in 1928, working on the reverse problem of how alpha particles, escape from radioactive nuclei, which is the same barrier crossed in the opposite direction. Because a particle is a wave, its position is not confined to where classical mechanics says it must be. The wave function does not stop dead at the edge of an energy barrier. It decays into the barrier exponentially. And if the barrier is thin enough, a small but non-zero amount of the wave emerges on the other side, which means there is a real probability that a proton which does not have enough energy to climb the barrier will simply appear beyond it. This is quantum tunneling. It is not a metaphor, and it is not a loophole. It falls directly out of the fact that particles are described by waves that cannot be sharply confined. The probability for any given proton pair is fantastically small. But the core of the sun contains something on the order of 10 to the 56 particles, and they collide constantly and over billions of years. The small probability multiplied by the enormous number gives a steady, gentle, self-regulating burn, which is incidentally why the sun is stable rather than explosive. If fusion were easy, the sun would have consumed itself in a very short time. It is the sheer improbability of tunneling that makes stellar lifetimes long enough for planets to cool and oceans to form and life to get started. So take a moment with this. Every photon that has ever warmed your face, every summer afternoon, every green leaf on every tree, the entire energy budget of the biosphere, all of it exists because of a rule that lets particles be where they have no right to be. The sun shines by breaking a classical law that was never really a law. And if you look at it from the other direction, the fact that you are lying here at all in a warm room on a planet with liquid water in a universe old enough to have produced carbon and oxygen in the cores of dead stars depends on Planck's constant having very nearly the value it has. Nudge it and the barrier penetration changes and stellar lifetimes change, and the whole story runs differently or not at all. The number Planck introduced in 1900 as an act of desperation is one of the dials the universe is set on. There is a common feeling about quantum mechanics that it is exotic, that it belongs to laboratories and particle accelerators and thought experiments about cats, and that ordinary life goes on above it, unaffected. I would like to dissolve that feeling because the opposite is true. You are surrounded tonight by machines that could not exist without it, and most of them are within a few meters of you. Start with the one you are almost certainly holding or lying near. In December of 1947, at Bell Telephone Laboratories in New Jersey, John Bardeen and Walter Bratton, working in a group led by William Shockley, pressed 2 gold contacts against a piece of germanium and observed amplification. It was the first transistor. A transistor works because of quantum mechanics from top to bottom. Semiconductors have the properties they do because of band structure, which is what happens to the allowed energy levels of electrons when you arrange atoms in a repeating lattice. There is a gap between the band where electrons are bound and the band where they can move freely, and the size of that gap determines everything. Doping the crystal with tiny amounts of other elements shifts the availability of carriers. The junction between differently doped regions creates a barrier that can be controlled by a small voltage. None of that language exists in classical physics. Bands, gaps, holes, carriers. These are quantum concepts describing quantum objects. The device you are using tonight contains, depending on what it is, somewhere between a few billion and 100 billion transistors, each one a few tens of atoms across in its critical dimensions. And at those sizes, quantum tunneling stops. being an asset and becomes a nuisance. Electrons leak through insulating layers that are only a handful of atoms thick, and an enormous amount of engineering effort goes into managing that leakage. The chip industry has spent decades fighting the uncertainty principle and mostly winning. Flash memory, on the other hand, uses tunneling deliberately. To store a bit, electrons are pushed through an insulating barrier onto an isolated island of conductor, where they sit, unable to escape, until deliberately removed. Every photograph you have ever saved on a phone is a small population of electrons that were made to be somewhere they could not classically go. Then there is the laser. The principle was written down by Einstein in 1917 in a paper on the quantum theory of radiation. He showed that an atom in an excited state, struck by a photon of exactly the right energy, will be stimulated to emit a second photon, identical to the first, traveling in the same direction with the same phase. Stimulated emission. Two identical photons where there was one and then four, and then a cascade. It took 43 years for anyone to build one. Theodore Maiman at Hughes Research Laboratories in California fired a synthetic ruby rod in May of 1960 and produced the first laser light. His paper was rejected by Physical Review letters as insufficiently novel, which is one of the great editorial misjudgments. Lasers are now in the scanner at the supermarket, in the fiber optics carrying this audio to you, in surgical theaters, in the disk drives some of you still own, and in the interferometers at LIGO that detected gravitational waves from colliding black holes in 2015 by measuring a change in length 1/10,000th the width of a proton. Then there is magnetic resonance imaging. Protons have a quantum property called spin, and in a strong magnetic field, their spin states have slightly different energies. Hit them with radio waves at exactly the right frequency, and they flip between states, and when they relax back, they emit a signal. Because the resonant frequency depends on the local magnetic field, applying a carefully shaped field gradient lets you work out where in the body each signal came from. An MRI scanner is a machine for interrogating the quantum states of the hydrogen nuclei in your own water and reconstructing a picture of you from their answers. Millions of people are alive because of a diagnostic technique that is applied quantum mechanics from beginning to end. And then the clocks. Since 1967, the second has not been defined by the rotation of the Earth. It is defined as the duration of 9,192,631,770 oscillations of the radiation, corresponding to a particular transition in a cesium-133 atom. That number is not arbitrary in the way it looks. It is the frequency of a specific quantum jump, and it was chosen to match the old astronomical second as closely as possible. And it is used because that transition is identical in every cesium atom in the universe, forever. Atoms do not wear out or drift. They are, as far as anyone can tell, perfectly identical, which is itself a quantum fact. Every satellite navigation system on Earth works by comparing the timing of signals from satellites carrying atomic clocks. If those clocks drifted by a millionth of a second, your position would be wrong by 300 meters. So the thing that tells you where you are and the thing that decides what a second is are both quantum devices. And then there is the thing that is not quite here yet, and which is worth understanding properly because it is described badly almost everywhere: quantum computing. An ordinary computer works with bits, each of which is definitely a 0 or definitely a 1. A quantum computer works with qubits, which can be held in superpositions of 0 and 1, and which can be entangled with one another. The popular explanation of what this buys you is that a quantum computer tries all possible answers at once in parallel. That explanation is wrong, and it is worth replacing because the truth is more elegant. A machine with a few hundred qubits does indeed have a state described by an astronomically large number of amplitudes, but you cannot read them out. When you measure, you get one answer, chosen probabilistically, and everything else vanishes. Simply running every possibility at once and looking would give you a random result, which is useless. The trick is interference, and we've already met it at the double slit. A quantum algorithm is a carefully choreographed sequence of operations designed so that the amplitudes corresponding to wrong answers cancel each other out, the way crest meets trough on the dark bands of the screen, while the amplitudes for the right answer reinforce. You are not searching. You are arranging for the wrong answers to destroy themselves so that when you finally look, the right one is overwhelmingly likely. Writing such a choreography is extremely difficult, and only a handful of genuinely useful ones are known. The most famous was found by Peter Shor at Bell Laboratories in 1994. It factors large numbers into their prime components efficiently. That sounds like a niche mathematical exercise. It is not, because the difficulty of factoring very large numbers is what secures a great deal of the encryption currently protecting banking, messaging, and government communication. A sufficiently large, sufficiently reliable quantum computer would break it. Nobody has built one. And the gap between the machines that exist and the machines that would be needed is very wide. Real qubits are appallingly fragile, for exactly the reason we discussed earlier. The moment the environment learns anything about their state, decoherence sets in and the delicate interference is ruined. Current devices operate at a few thousandths of a degree above absolute zero in shielded vessels, and their states survive for fractions of a millisecond. The route around this is quantum error correction, in which many physical qubits are used together to encode one much more robust logical qubit. In late 2024, a team at Google reported a chip on which increasing the size of the error-correcting code actually reduced the error rate, which is a threshold that theorists had identified decades earlier as the point at which the approach becomes viable. That is a genuine milestone, and it is also a long way from a machine that factors anything anyone cares about. Serious estimates of what a cryptographically relevant machine would require run to millions of physical qubits. Meanwhile, the defensive side is already moving. Cryptographers have developed encryption schemes based on mathematical problems that quantum computers are not known to solve efficiently, and standards bodies have begun issuing them. The concern is not really about the future. It is that encrypted traffic intercepted and stored today could be decrypted decades from now, which means anything that needs to stay secret for a long time needs to be protected now. There is also a use of quantum mechanics for the opposite purpose, and it is already operational. Quantum key distribution turns the fragility into a feature. There is a theorem proved by William Wouters and Wojciech Zurek in 1982 stating that an unknown quantum state cannot be copied, not because we lack the technology, because copying is mathematically forbidden by the structure of the theory, which means that if two parties share a key encoded in the states of individual photons, any eavesdropper attempting to intercept and read those photons must measure them, and measuring disturbs them, and the disturbance shows up in the statistics when the two parties compare a sample of their results. You cannot listen without leaving fingerprints. The protocol was devised by Charles Bennett and Gilles Brassard in 1984, and systems based on it have been deployed over fiber networks in several countries and demonstrated between a satellite and the ground, So a rule about what nature will not let you do turns into a guarantee that nobody can be reading over your shoulder. Estimates of how much of a modern economy depends on quantum mechanics vary and are inevitably rough, but the honest answer is that essentially all electronics, all telecommunications, all modern medicine, and all precision measurement rest on it. It is not an exotic corner of physics. It is the floor. There is one more thing this layer has done, and it is the largest thing anyone has ever attributed to it. And I've saved it for last because it is the one that connects the smallest scale to the biggest. The quantum world made the galaxies. Let me walk you into that slowly, because it sounds like an overstatement, and it is not. Look at the universe on the largest scales we can survey. It is lumpy. There are galaxies, and galaxies gather into clusters, and clusters string together into filaments and sheets with enormous voids between them. Structure everywhere. Now look at the oldest thing we can see, which is the cosmic microwave background, the faint bath of radiation left over from about 380,000 years after the beginning, when the universe first cooled enough for light to travel freely. It comes from every direction, and it is the most uniform thing ever measured, almost perfectly uniform, but not quite. The COBE satellite, launched in 1989, found the deviations in 1992, and George Smoot and John Mather received the Nobel Prize for it in 2006. WMAP and later the Planck spacecraft mapped them in exquisite detail. The variations are about 1 part in 100,000, regions very slightly warmer and very slightly cooler, which is to say very slightly denser and very slightly less dense. Those tiny density variations are the seeds. Gravity is patient and relentless, and over billions of years, a region that starts marginally denser pulls in a little more matter, becomes denser still, and pulls harder. Every galaxy, every star, every planet, every atom in your body grew out of one of those faint irregularities. So the question becomes, where did the irregularities come from? If the early universe had been perfectly smooth, it would have stayed perfectly smooth. Gravity amplifies differences. It does not create them from nothing. Something had to put the initial ripple in. The leading answer comes from the theory of cosmic inflation, proposed principally by Alan Guth in 1980 and developed by many others. It says that in the first unimaginably brief instant, very much less than a trillionth of a second, the universe underwent a period of exponential expansion, growing by an enormous factor in almost no time at all. And here is where the two ends of physics meet. Before inflation, the region that became our entire observable universe was smaller than a proton. At that scale, quantum uncertainty is not a small correction. It is dominant. The fields filling that region could not be perfectly uniform because uncertainty forbids it. They fluctuated constantly, the way any quantum field does, with tiny random variations appearing and vanishing. Then inflation happened, and it stretched space so violently and so fast that those fluctuations were pulled apart faster than they could subside. A ripple that would have flickered out of existence in a fraction of an instant was instead dragged out to a size larger than the region could communicate across, and it froze in place. Quantum noise stretched to cosmic dimensions and then made permanent. Those frozen ripples are the density variations. They are what COBE measured. They are what became the filaments and the clusters and the galaxies, which means that the arrangement of the entire visible universe, the reason there is a Milky Way here rather than uniform thin gas, is a photograph of quantum fluctuations from the first instant, enlarged by a factor beyond ordinary comprehension and preserved for 13.8 billion years. The pattern of light in the cosmic microwave background is the uncertainty principle written across the whole sky. I want to be honest that inflation is not proven. It is a strong and successful framework. It makes predictions that have been confirmed, particularly about the statistical character of the fluctuations, and it is the leading account by some distance. But it is not settled in the way that the double slit is settled, and there are serious cosmologists working on alternatives. This is a live area, not a closed one. Still, if it is right, and most of the evidence points that way, then the story of tonight has a shape that is hard to improve on. A rule about the smallest possible things, discovered by a reluctant man trying to explain the color of a hot furnace, turns out to be the reason there is anything at all arranged in the sky. The largest structures in existence are the fossils of the smallest possible events. And now, having said all that, I want to end the technical part of tonight with a confession. We do not know what any of it means. That is not a rhetorical flourish. It is the plain situation, and it has been the situation for 100 years. The mathematics of quantum mechanics is the most precisely tested theory in the history of science. One quantity, the magnetic moment of the electron, has been calculated from quantum electrodynamics and measured experimentally, and the two agree to something like 12 decimal places. That is roughly the equivalent of measuring the distance from London to New York and getting it right to within the width of a human hair. Nothing in science has ever been confirmed like that. And yet there is no agreement whatsoever about what the theory is telling us about the world. There are several serious interpretations, all of which make identical experimental predictions, which is precisely why the argument cannot be settled by experiment. The oldest is usually called the Copenhagen interpretation, associated with Bohr and Heisenberg, though it was never a single fixed doctrine. Its rough shape is that the wave function is a tool for calculating probabilities, that measurement causes it to collapse to a definite outcome, and that asking what the system was doing between measurements is not a meaningful question. It is a practical, disciplined, slightly austere position, and it is what most physicists were taught, and it is often summarized, unkindly but not entirely unfairly, as an instruction to stop asking. Then there is the many worlds interpretation, proposed in 1957 by Hugh Everett, a graduate student at Princeton working under John Wheeler. Everett's move was to take the Schrödinger equation entirely seriously and simply delete the collapse. If the equation always applies, then a measurement does not select one outcome. It entangles the observer with the system, and every outcome occurs in branches that decohere from one another and can never subsequently interact. There is no special measurement process because there is no collapse to explain. It is either the most economical interpretation or the most extravagant, depending on whether you count equations or universes. Everett's reception was cold. Bohr's circle dismissed it, and Everett left academic physics entirely for a career in defense analysis. He died in 1982 at the age of 51, having lived to see his idea begin to be taken seriously, but not to see it become, as it now is, one of the leading positions among physicists who work on foundations. Then there is the pilot wave theory, developed by David Bohm in 1952, building on an earlier proposal by de Broglie. In this picture, particles do have definite positions at all times, and they are guided by a real physical wave. It restores determinism, and it restores particles with trajectories, and it reproduces every quantum prediction exactly. The price is that it is explicitly non-local. The guiding wave depends instantaneously on the configuration of the whole system, which is exactly what Bell's theorem says any such theory must be. Then there are objective collapse theories, in which the wave function really does collapse, but spontaneously as a physical process, with a tiny probability per particle per unit time that becomes overwhelming for large objects. These are interesting because, unlike the others, they make slightly different predictions, and experiments are slowly closing in on them. And there are others. Relational quantum mechanics, cubism, in which the wave function represents an agent's beliefs rather than the world, consistent histories. Surveys of physicists at Foundations conferences produce genuinely split results, with no interpretation commanding anything like a majority. 100 years. 12 decimal places of experimental agreement, and no consensus on what the theory says about reality. I find that oddly comforting, and I want to tell you why before we let the night close in. There is a way of presenting science as a finished thing, a body of settled facts to be learned, handed down complete. And that presentation makes people feel small because it positions them as receivers of something already known. The actual situation is nothing like that. The actual situation is that 100 years ago, a group of people in their 20s and 30s working in Copenhagen and Göttingen and Cambridge and Paris and Zurich found a crack in the world and followed it down. And what they found there was so strange that they argued about it bitterly for the rest of their lives and never resolved it. And their successors have not resolved it either. And the crack is still open, and anyone who cares to can go and look into it, and the looking is not finished. Planck did not want to find what he found. Einstein spent his last 30 years objecting to a theory he had helped create, and his objections were so precise and so well constructed that they eventually generated Bell's theorem and a Nobel Prize awarded 70 years later. Being wrong in an interesting way turned out to be one of his greatest contributions. Schrödinger invented an argument against the theory, and it became the theory's most famous image. Bell worked on it as a hobby because it was not respectable and settled a question everyone had thought unanswerable. None of them knew what they were doing while they were doing it. They were simply paying very careful attention to something that did not fit and refusing to look away. Let me leave you there gently as the night gets late. You are lying in a room, and the room is quiet. Beneath you, in the mattress and the floor, and the ground below it, uncountable numbers of electrons are refusing to share their states, and that refusal is the only reason you are not sinking through everything, all the way down. Inside you, in every one of your cells, electrons are moving between energy levels in molecules, and the exact spacing of those levels is what makes chemistry work, and chemistry is what is currently keeping you alive without any effort on your part. If there is any light in the room at all, it is arriving in packets, each one carrying a small definite amount of energy determined by its color and by a number a Berlin physicist wrote down in 1900 without believing in it. And 8 minutes journey away, in the middle of a star, protons that do not have enough energy to touch are touching anyway, because the rules permit a wave to be a little bit where it should not be. And the light that pours out of that is what warmed the ground today, and what grew everything you ate, and what has been holding this whole small blue arrangement together for 4.5 billion years. None of it needed you to notice. That is the thing I would like you to take into sleep, if you are still with me at all. The layer beneath reality is not waiting for us, and it is not about us. It was running with perfect consistency for 9 billion years before the Earth condensed, and it will run for a very long time after. We are simply large enough and warm enough and thoroughly enough entangled with everything around us that it has become invisible from where we stand. But it is there, under the bed, under the floor, under the whole world, quiet, exact, and completely indifferent to whether anyone is looking. Let your breathing go slow. The room is holding together. The atoms are keeping their distance. The sun is doing something impossible. Out beyond the window, in the dark. Sleep well.